Hello guys, my name is Max, and welcome to this video today. We're going to continue to develop our tic-tac-toe game using JavaScript and HTML. So we left last time, if we open this up in a browser, we just got the basic sort of interface of the game going, so we can click on the tiles to like flip them, and we alternate between the north and the cross tile like this to play a two-player game, so to speak. So today we are going to implement AI to this game, and then in the next video we'll implement the menu or sort of the interface, so we can change between the different game modes as we so choose. So the algorithm we are going to use is more or less just taken directly from this article here. That is describing AI player in Java code, and the min-max search algorithm. So basically what the min-max search algorithm is, it is a recursive algorithm that sort of calculates the gain for all possible moves from any given sort of game or playboard or any given game state. So it calculates all the sort of like free cells, all the free positions, and calculates how possible it is for it to win if it moves to that cell, or how possible it is for it to lose if it moves to that cell. So that's sort of the algorithm in a nutshell here. Yeah, so you can see here we search through all the sort of moves that are all legal moves for the current player here, and then we have this sort of recursive algorithm here. So we have the base case here, if it's game over or the level is 0 on the search level, then we return. Also we run this code here recursively, and here's the recursive step right here, where it should be, here and here is the recursive step, of course. Then it will return the best score here. And as for our purposes, it will also be quite important to return the move or the index for where we want to move in order to like update the game state. So without any further ado, let's get started. So we can start by going down to the bottom of the script file, sort of right here, and we can define a new function or class here that we will call AI player. So call it set like this, and as sort of the argument here for the constructor, it just take the data with the current game board, and then we just save that to this data variable here that we can use inside this function. Then we will need a seed and the seed of the opponent, and these are just let's say what sort of tile the AI and the player or the computer and the opponent player is. So we need a function to set the seed. So you say this.set seed equal to a function like that, and then we need a function to get the seed. So we say this.get seed like that. And then we'll use a move function like that, and then we have some private functions here. So we have the min-max function like that, and that's to depth and player as augments there, as it has in the article as well. Well, I close that down, but whatever. And then we'll need some evaluation function to like evaluate each of the different moves here. Yes, so we need a function evaluate like that, and that will need a helper function that we'll call evaluate line like that. And then lastly we'll have another public function here that we'll call pass1, and that will also calculate if a particular move yield a win for for a player, or if the current game board is equal to a win. And that will need this private field here that we call winning patterns. And that will just be equal to this self-invoking function here, so we will initialize it inside of here. And that we'll use inside of this has1 function. And that of course take the player of which to check against who has won. So let's start and implement those functions in a bit random order maybe, but we can start with the simple ones. So we can start with the setSeed function. So that we just take this seed parameter like that, and then we'll say that seed is equal to this seed, and then we take the opponent seed is equal to the seed if that's equals to the tile north. Then we want it to be tile cross, else we want it to be tile north, of course. So we can get an instance of each of the different seeds right there, and then we get seed, we will just return the seed like that, and then the move function, it will just return the minimax of the depth search of, let's say, 2, and the one we want to search against is the seed, of course, and we want to return the second field there, because this minimax function we're going to run an array list with the move, or the index we want to move to, and as the first argument here, the best score, or the best the current score for that particular move. We haven't implemented yet. So starting to get shape here, so just so we don't have any syntax error. So this early in the development, let's just go up to the init function. Let's just create our AI, and we can create that as a new AI player like that, and then we can set the seed. We can say here, we can say player. We won't set to the opposite of the player, of course. So say if the player is the tile north, as it is in this case, then we want to be cross. Also want to be tile north, so we have that done like that. And just to make sure that we specify the global variable of AI right there. We have that done, so let's just log out console log ai.getSeed just to see if it works here. Yeah, so that's logged out the image, or the the image or the seed that we currently have there. So that's good. So everything's working so far. Speaking of global variables, I think we had an error in the last video where I write here. So this should of course also be a variable here. This shouldn't be populating global scope, which it is if we don't specify the var keyword in front of this variable right there. Anyway, moving on to this function here. Yeah, so the minimax algorithm, it basically works as we said before here, that it looked through all the current moves, all the valid moves. So we'll just call that next moves, something like this, and we can set that equal to the get moves function, and that we forgot to implement here. So let's just implement that right here. So say function. This was in the wrong function as well. Okay, sorry. Bar next moves equals get moves, or get valid moves, maybe you can call it like that, get valid, and we can implement that just right here. So say get valid moves. Yeah, brilliant. So it will sort of just let's open this up again. Let's see here. Yeah, so it will look through all of the value moves, and then it will run this code here. Yeah. So let's implement that. Let's see. Let's open this up again. So if we want to do that, we'll need some fields here that we'll keep track of. So we'll have the best field here, so the best score, or the current best score here. And then we say if the player, if the maximizing player, so if it is the AI opponent, then we want it to be some small number to the start there. So I'll just use minus a large number right there. Also, we want it to be a big number if it is the minimizing player, so to speak. So a small number if it is the maximizing player, and a big number if it is the minimizing player. And then we need to keep track of the current score, and I will just leave specifying declare that variable right there. And then we'll need the best index field right there, and we'll set that to -1 to the start. We will just return that right there. So then we know if we can't move anywhere, that means the board is full, and that means, so, and then it will turn -1. So we know that. So we know if this function, minimax function, or this move function rather, return -1, then we know that the board is full. Anyway, so we say if the next moves, the length is 0, so if one of the players won, something like that, then there are no valid moves left, or the depth is 0. So if we have traversed down the minimax search tree down to the depth of 0, then we just take the best to the, then we evaluate the score of the board of the current game state. Else we want to do this sort of recursive algorithm here, so we say for I equals the next moves.length, like that, and we can use this shorthand syntax just looping through all of the next moves, and we can call that m here, so we say next moves at I, like that, and that should give us our number, or what index we can move to. And then we call this, we set the data at that particular cell equals to this player variable. And for that to work, we'll need this set function. So let's just implement that. You can do it right over the flip. Let's say this the set function next, and it will work quite similar to the flip here, just that it will just set the child equal to next, like that. Yeah. So this is sort of this step right here. So we say if the where are we? Yeah, we try to move for the current player, so to speak. So we set, and then we check how that influence the game board. And then after we do that, we set it back to the blank tile for now. Because if it is a valid move, then that means that the tile is blank. Okay, so here we'll do the different checks here. So say if the player is the AI seed, like that. Also it is the sort of the player seed and not the computer seed. So then we'll do two different algorithms here. So we set the current to the minimax of the depth level -1, and then the opponent seed, and we want to set it to the score field that we return right there. Then we say if the current is greater than the best, then we want to set the best equal to the current, like that, and then we set the best index equal to the m to the move right there. And the same go for this one, but we do it in the other direction. So we say minimax depth -1, and then we want to take the seed here. And then we say if the current is less than the best, Then we want the best equal to the current, and the best index equal to n. So that's all of the minimax functionality of the function. So our L3 we want to implement now is this get value moves function, evaluate and evaluate lines, and then winning patterns and has one function, and then we should be done with the AI system. So we can start with the get value moves. That's simple enough. We can just create this next move list here, nm for short. Then we say if has one seed or has one player, or sorry, opponent seed. So if the computer or the player has one, then we just want to return an empty array or empty list, nm like that directly. Else we just want to loop through all the indexes in the data variable or in the data array. So we say I use this shorthand for loop again. Then we say if the data at the I position not has any data in it, like that, then we want make to push that index to the sort of, let's see here, let's write this. Then we want to push that index to the next moves array here. So if it is blank, that's basically this function which returns if the tile is blank or not. So we say if the tile isn't blank or is blank in this case, since we negotiate or take negative evaluation of this expression. And then we just push that index to the to this array here. So that's we'll get all the value moves right there. Now we will just do the evaluate function, and that's a bit boring maybe. So we will calculate our score value here that we will return like that, and then we just we'll evaluate every line, all of the 8 different possible wins in. So if we just let's see if I can find this right here. So we say, let's say here. So here's is how the indexes of this is sort of the indexes of all of the of the game board here. So we have 0, 1, 2, 3, 4, 5, 6, 7, and 8. So basically the ways you can win, or the lines you want to evaluate, is you can, if you this line here, this line here, and this line here. So this is all the different lines you can win. You can win on all of the horizontal lines, all of the vertical lines, and also the 2 diagonal lines. So 8 lines in total that we want to evaluate. And if we look through this here, so the first line, that should just be at the index 0, 1, and 2, like that. Then we can just copy this down 7 times. Let's actually do it like this. So say evaluate line, like that. 3, 4, 5, 6, 7, 8, I think. Yeah. Anyway, and then the second line, that should be 3, 4, 5. Of course, if you look here, 3, 4, 5. Then we have 6, 7, and 8 for the last horizontal line, and then we begin with all of the vertical lines. So that will be 0, 3, and 6. The first vertical line, 0, 3, and 6, and then 1, 4, and 7, and 2, 5, and 8. So let's say 1, 4, and 7, and 2, 5, and 8. Then lastly, do we have 0, 4, and 8, and 2, 4, and 6. So 0, 4, and 8, and 2, 4, and 6. So that's all the lines we want to evaluate. Now let's just implement this function. So you say index 1, index 2, index, and index 3. They're the 3 different indexes we want to check. And here again, we calculate this. And we declare this score function, or score variable, that we return. So we return s, that's to score in this case. Then we just want to check against all the lines. So we say data index. We can put it like this for now. Now we say if that's equals to the opponent seed, like that. Else if the index is equals to the sorry, I got this in the wrong direction here. The seed or the opponent seed, this is how it should be. And then we want to check against all 3 different seeds here. So we say right there, and then we specify, let's say 1, 1 here, 2, 2, and 3, and 3. Yeah. So we need to implement this equals function. So let's do that first, and let's just say it right here. So we say that's the equals function tile return tile equals to tile. Yeah, so that's equal function. Yep, so have that done, and then basically right here comes the evaluation functionality of it. So basically what we want to do, it's all the way up here. So we say we want to give it +1 if it is 1 in a line. Also we want to give it if it is the computer or the current player, and we want to give it a -1 if it is the opponent player. So that's simple enough. So we say if it is the player, then we want to set it to 1. Also we want to set it to -1 to the first if we have 1 in a line. Then we want to check if we have 2 in a line. So here we can say if s is equal to 1, then that means that we have 1 in a line but previously here. So then we set s equals to 10, like that. Then we can say else if s is equal to -1, then that means that the previous tile in that line was occupied by the opponent. Then we want to set the s to 1, of course, since we only want to have 1 step. Or then we only have 1 in the line again. Then we have the else here. That means that the previous tile was empty. The tile we checked against up here. Then once again, then we set it to 1. Here we just want to return 0 if it isn't really necessary for us. Yeah, here we have it's the 0 otherwise here. Yeah. So that's basically it. So then we do the same for the opponent here. So, but of course we change this to -1 here, this to -10, this to 1, and this to -1. So we have that done. Then the last index is a bit more complicated here, but basically check if the value is over 0, then we want to multiply the s by 10 here, because that means that the second child was the seed, or that the first tile and the second tile was the seed. So this will be this here will be evaluated as true if this or this was called, right? This or this. So all those 3 cases. Then we have the else if s is smaller than 0. So that means that the 2 last indices was occupied by the opponent. Then we just want to return 0 again. Then else we just set s to 1, because that means that we have 1 in a row again. And then we once again can just copy this down for this one, and then we just change direction of those 2, and then we just take negative right there. And that is the evaluation function. So the last thing to implement is this has one function, then we should have a functioning AI system. So for this one, it is a bit complicated. We will use bit masks in order to speed up the process here. So we'll define all the the bit masks right here. So you say, and basically what the bit mask is that you use bitwise operations to like compare different strings of text. And if you don't know really what bitwise operation work or how they are, please leave a comment in the description. I'll try to explain it for you, and I will leave some kind of link to it in the description as well. And basically we want to check. We have 9 indexes in the data board, of course. And basically, so we have where like now we can use 9 bits for that. So you can use a number with 9 bits, or that probably like 2 bytes or something. I don't know how the computer will allocate memory, but that doesn't really matter. That's what's matter is that we take this bit string and evaluate it as a number, of course. Now we can use bit masks for like controlling if that's tile is to compare if we have a one case, that is. Anyway, so we have all of the horizontal lines here. So say like this. Then we have all the vertical lines. So that should be like that, and lastly like that. And then we have the 2 diagonals as well. So we have that one, and then we have that one. So that's all of the different diagonals, and that's sort of this is the exact same thing as we have up there, or the same concept at least. Okay, so we have the winning patterns, and then we want to just evaluate those as numbers and not as strings. So we can use the parseInt method that is built into JavaScript, but for that we'll use this array here that will initialize to a specified length here. Then we just loop through all the different winning patterns here like that, and then we just parse integer here with the two arguments. So the first one is the string we want to pass as an integer, and just so this integer here, for example, or this string of text, we don't want that to be evaluated as 111, but we want it to be evaluated to 7 or something like that. So for that we can use which sort of base system we want to use here. So if we have use base 2, then that means that we'll evaluate it as a bit, as a string of bits, and not as a base of 10. So if it should have put 10 here, then we will evaluate it by the base of 10, and we should get 111. But if we evaluate it by 2, then we will get 7 or something like that. I think that's a 1 plus 2 plus 4, so that's 6 plus 1, so 7. Yeah. Anyway, and then we just want to return R here. So that should give us this sort of string. And just to see if it works, let's just log out R here, so you can see what that looks like. Let's see, 328. That should of course not be if, that should of course be for. Yeah, so here we can see that, for example, this was evaluated as to 7 as I said, but let's say we have base of 10, then we should get 111. Yeah, then we can see that we get like this, but that's not what we want. We want them as evaluated to bit strings, as bit strings like that. So since we're using this here, then we basically want to use up here we have has one So we'll set that both to like a local and a public function. So let's say bar has one there to give it to the local scope as well. Anyway, so the hasFun function is quite boring, but yeah, anyway, let's implement it. So it's basically what we do. We declare this pattern variable here that I will just call p for short, and then we loop through all of the different, all of the indexes in the data array. So we say data.length I minus minus this shorthand here to loop through all of those things again, and then we just check if the data at I is equals to the player that we specify as an argument to this function, right there, and then we use a bitwise OR to compare that to I bit shifted to 1, bit shifted by I. So what this sort of mean here? So an OR operator in a bitwise context means, so let's say you have, all numbers in computer memory that are defined as bit strings like this, or strings bits. So for just convenience, let's say p is equals to 0, then that is allocated in memory by those 3 bits. They're probably like 32 bytes or something like that in real memory, but whatever. Just for convenience, let's say 3 bits, and let's say 1. And let's say we have just 1 here. So then we have p, that is 3 bits of 0, and then we say and equals or equals 1, that is this in bits, so it's 2 zeros and then a 1. Then that will be evaluated as 0, 0, 1, since sort of like they compare all of the positions in the bits, and if they are 1 in one of the bits of that position, then the result will be 1. So for example, let's say we have this, that say p is equal to this, and then we or equals that to that bit, then that will be evaluated to that. The same goes if we have a 1 here, then this won't be 2 because bits are only 1s and 0s, so this will still be 101, like that. And the bit shifting in the whole thing here, so let's say once again we have 1, so let's say we have 1 represented by this bit string, and then we bit shifts that by 1, then that will be equals to 0, 1, 0, because we shift this bit's position by 1 to the, and this is the wrong direction, sorry, we bit shift that 1 to the left. And the same thing if we have 2 here, then we will bit shift it so the final string would look something like that. So basically what this will do, it will loop through all the indexes in the data array and check if that's equals to the player that we are comparing against. And if it is, then it will sort of save that position to this pattern here. And then we can compare this pattern using an AND operator, bitwise operator, to check if it is one of the winning patterns. I hope that makes sense. If you want more on this, please leave a comment and I'll try to explain it more in depth here. But anyway, so then basically what we do is we loop through all the winning patterns. So we say winning patterns length I minus minus again, and then we say var vp, this time winning patterns at I, like that. And then we say if the p and winning pattern is equals to winning pattern, then we want to return true, else we want to return false. So the AND operator, that works a bit similar to the OR here, or they sort of resemble the logical AND and OR operators. But basically, let's say you have p again, let's say p is equal to this bit string, or this string of bits, and then we OR that with the string that, then the result will be a 0, 0, 1, because it only copies position that has both ones in it. So let's say, for example, if this should have been a 0 right there, then this should be 0 like that. So if, for example, let's say we have a bit pattern that looks like this, but bit string was this, then the result should be this, and then those two things, this and this isn't equal, so this should be evaluated as false. So this is how bit masks work. This is the actual bit masks in use here. So that should be it. That should be the final AI system right there. So to check if it works, we can go up here to the init method or someplace, and here we can just log out. So we say console.log ai.move, and not to forget, let's just specify the data as an argument here to the constructor. And if this works now, let's see in the browser. Undefined is not a function. This.evaluate should only be evaluate, so line 224. Let's see here, 224. That should be like that. We don't really need to log out this message anymore. Let's see. Well, it was evaluated as 0. That shouldn't really be the case. Wonder where that can be. One moment, guys. Be right back. Yeah, so I basically found the error. This here, of course, shouldn't return the best index, or the current. We should say the score here, and not the sort of the move we want to move to, of course. So, but just change those ones here to zeros, and it should work fine. So you can see that the best move, apparently, at the start is to move to 4, which is in the middle of the tiles. So that sort of makes sense, for at least my intuition with tic-tac-toe. Anyway, so one final thing. Let's change the update method to work with our AI, so the AI actually work here. But for that, we'll need a couple of new variables, I think. So let's go up here to the top, and I will declare 2 Boolean variables that we will have calculated soon. So we can say is player, and we can say AI moved. So those 2 booleans. So we can declare them right here. So you can say is player. That's just equal to the player. If it is the north, so we always start with the north position, with the north, and then we can set the has move. Okay, sorry, AI moved to false here at the start, and let's just leave out that console.log message for now, and then we just update the mouse down event, and then right here we can say if it isn't the player, then we want to return, then we just don't want to register the mouse clicks. Then right here we will get rid of this that changed the player between the different between the north and cross. And then here we just want to set is player equal to false. So we have that done, and then basically everything else we'll do in the update method here. So first of all, we need to check if the flipping animation are done on all of the tiles. So here we can set this active anim variable. So active anim, so active animations, and we set that to false at the start here, and then here each time we check against update our tile, then we set the active animation here to the active animation or the data at i.active, like that. And the active procedure or method or function or whatever, here we just return this active equals function that just return if the animation variable here, so remember this is how we update, or how we check the variable we use for animation. So if the animation is 0, then that means that if it is bigger than 0, then that means that the animation is active. So to see if this works now, or if I got in the wrong direction, let's just log out. Let's just do it like this. You can see here, you can say if not an active animation. Let's just log out, test message for now. So we say test. Oh, come on. Yeah, finally. So let's see. So now we click on the tile. Yeah, we can see that the test stops validating like that. And I only can flip one tile then, because then I changed the isPlayer variable. So that works as well. So that's good. Okay, and then here we can just check if it isn't the player. Also, you can check if the AI has moved, rather. Like that. And it isn't the player. Like that. Then we want to move the AI. So you say AI.move. Like that, and remember, if it returns -1, then that means that it is a draw. So we check if m is equal to -1, then we just want to return for now. You can log out draw to the console, maybe console log draw. Like that. Else we want to flip the tile at the m position to the AI.get to the seed of the AI player. Like that. Then we want to set the isPlayer equals to true, like that, and we want to set the AI moved to true right here. Always like that. And then else we set the AI moved to false. And if we have done this correctly, we should now actually have a functioning game. So let's see. So if I flip this tile, then the AI flip that tile, then I say for example go there, yeah, and it blocks me, and it seems to be working here. And now if I put it here, you can see that the draw message is written out. So that means it works. So far so good. Basically one test we can do. Right here you can say let's actually not use, let's use, just use like this with console log draw. Let's see what it looks like now. It shouldn't be written over and over again in console, so let's see. Yeah, now we've all written out once, so that's what we want. Yeah, so that's it for this video, guys. So I'll leave it to this for now, and in the next video we will do the check against if we will check, or actually we can do it right here, I think. Let's see. So we can say if actually we want to do that before. I don't really know a smart way to implement this. Yeah, I will think about that to the next video, and I will leave it for this for now. So thank you guys for watching. See you guys in the next video. Bye.